So welcome to the webinar from ChemSec. I should start with saying that we will record this webinar and we will make that recording and the slides available for you afterwards, and we will send them out to everyone who is registered for the webinar. So I will start this webinar. What we will do is today talk about PFAS and alternatives to different PFAS functions. I will give a very brief introduction to ChemSec for those of you who do not know about us, and that will be extremely brief. And then we will have a set of different alternative providers talking about their alternatives to PFAS and how to develop them and the challenges they have had. We will have a set of different ones. We will talk about alternatives to technical textiles, F-gases within semiconductor manufacturing, but also from different energy solutions. And important to point out is that we have a Q&A function, and we will have a large Q&A section in the end of this webinar. So we will, after everyone has presented. So please use the Q&A function to post your questions, and we will try to answer as many as possible in the end on the Q&A. And again, we will make the slides and the recording from this webinar available online after the webinar in case you want to see it later or if you missed the webinar. And I should also point out that we're extremely happy to have 4 companies here today with us giving very interesting presentations regarding their alternatives to PFAS. So I would like to start with thanking all of our 4 speakers today for being here and sharing their solutions with us. And I will just briefly talk about ChemSec for all of you to know what we are. So we're a Swedish NGO. And we are working to reduce the use of hazardous chemicals. And we do that in a few different ways. We drive the political discussion on hazardous chemicals through being a stakeholder at all the relevant committees and through our connections to the European Commission and other authorities. And we challenge companies to improve their chemicals management because we think that this is very important to have the front-runner companies showing the way forward, how we can work towards reducing the use of hazardous chemicals. And in order to support these companies, we have a set of online tools to help these companies switch to safer chemicals. For example, the SIN list, which is a list of chemicals we think should be banned, or Marketplace, which is an online platform for safer alternatives to hazardous chemicals. But we also work on the investor side, where we talk and inform investors about risks and opportunity in the chemical industry. But one of the most important part of our work is about alternatives and how alternatives can be used in order to substitute hazardous chemicals. And we talk a lot about the availability and the viability of different alternatives. And that's sort of the thing that we want to talk about today. And that is what the presentations today will be about. So we will have 4 different presentations from 4 different companies. And after that, we will have time for a Q&A, as I said before. And without further ado, I will hand over to our first presenter today. Comes from Ionomer Innovations. So Ben Britton, please, you have the floor.
It's very nice to meet you all and a pleasure to be here today. I'm Ben Britton. I am a co-founder and the Chief Strategy Officer of Ionomer Innovations. Next slide, please. And we're a team of 50 employees. We're venture-backed and have been out since 2018 based on 2 platform materials technologies that replace uses of PFAS materials in proton exchange membranes and bringing to market a new advanced material set in anion exchange membranes, which allows for the alternative use case to PEM-based electrolyzers, so proton exchange membranes based on chlorinated materials. And there was over a decade of research prior to commercialization. Next slide, please. We've been recognized by the Global Clean Tech 100, Deloitte, and the World Economic Forum, as well as Shell Game Changer with NREL. Next slide, please. And the FCell, we became the first Canadian company recognized for advances in fuel cell chemistry. And these are considered intractable uses of PFAS materials today, really replacing the fundamental basis material set at the very core of fuel cells and electrolyzers These same types of systems are used in flow batteries and other key energy systems, as well as sensors and other applications similar. And in every case, this is what drives the durability and is responsible for at least 80% of the resistance of these types of systems. So they really drive the efficiency as well. These are critical game-changing materials. And if you do not use the PFAS today, alternatives have considered to be not viable in the past. Next slide, please. And this is because there's an incredible design challenge in ion exchange materials. They function very much like cell membranes in your cells, and when you change any of their properties, it impacts all the other properties, all of which are critical for end device function. Next slide, please. And it's not just the polymer development, which is what has been focused on, and alternatives have been raised for over 30 years. It is the actual composite itself. So these membranes never act as a polymer alone. They have a number of related additives and composite reinforcements, all of which have to go into end device testing. And so we're one of the very few companies that has ever managed to put together iterative design for these types of applications. Next slide, please. And so again, we are focused on green hydrogen systems, so replacing PEM electrolysis and heavy-duty fuel cells, where we've passed the accelerated stress tests and the Department of Energy established means for this type of application. And then for hydrogen, we're exceeding the 2024 and meeting the 2030 targets that the EU has set for this technology, as none of the other energy agencies have set targets. Next slide, please. And this is a critical challenge because by 2050, these three target verticals alone could offset the entirety of global mobility, or the offset of North America, for further context. And this is very necessary as the target to electrify everything is incredibly challenging. 78% of energy today in the United States is molecule-based, and you can use, through hydrogen systems, the existing natural gas infrastructure in Europe and North America incredibly effectively. You should look up the European hydrogen backbone. Next slide, please. And these are on the same exponential trajectory as when wind and solar became cost effective. So these are critical technologies to the energy transition. Next slide, please. And these are based off of essentially superacid Teflon. So a PTFE backbone with a side chain sulfonic acid. And when you cleave that side chain sulfonic acid, you have a molecule that is very much in the same category as PFOS and has the same properties, and this is measurable. Next slide, please. And so as a result, we believe that this is not going to pass any sort of alternative. If the proposed legislation is going to restrict any category, it should restrict these sulfonic acid materials. You can literally measure this in electrochemical devices, and I have myself, and W.O. Gore has admitted to this as well. There are well-known established degradation mechanisms, many of which put out PFOS-like materials. Next slide, please. Next slide, please. And we can meet all of the targets for durability and performance, as well as having a green chemistry for the green revolution. Truly, these materials are producible in Europe under current REACH regulations, which is a critical milestone. This also makes them more scalable. So current PFAS-based materials are on a 1 to 2 year lead time. We can actually scale this technology markedly faster and have a faster energy revolution on the back of hydrocarbon materials. Next slide, please. And we have cleared out the historical challenges, in particular oxidative degradation, which was thought to be an impossible task. This was a statement by GM itself in a perspectives paper, and we have established that this is possible by a complete redesign of the molecular strategy. Next slide, please. And the conductivity, which is a measure of the efficiency of the system, can be markedly more effective in all conditions. This is measured at room temperature, but at high temperatures, we exceed the conductivity of PFSA-based materials. Next slide, please. And we can also exceed the performance in real devices through our subsequent generation of composites. Next slide, please. And we can pass the Department of Energy fundamental polymer stability test. Next slide, please. And we can also pass the integrated chemical and oxidative mechanical cycling test by a factor of 2 with our second-gen composites. Next slide, please. And even in fully hydrocarbon systems, so replacing both the membrane and the ionomer in the catalyst layer, which is also critical for function, we can achieve over 1 watt per square centimeter. This is relevant to heavy-duty vehicles and really takes us within the last couple of years on performance of the entire system. Next slide, please. And so these are available, and we go all the way through reference design systems to make integration of full systems easy. Next slide, please. Next slide, please. For AM electrolysis, we enable an alternate to PEM water electrolysis systems. We could make PEM water electrolyzers. However, in reality, AEM electrolysis is a better technology. It enables scaling of green hydrogen electrolyzers without iridium, which is a critical parameter, as well as without PFAS. So again, you can scale this faster and markedly more cost effectively. Next slide, please. And this traditional alkaline systems have a challenge of being efficient. Really, it's a compromise with safety factor, which is not anything that anybody wants to do. And PEM systems really is the scalability challenge on 2 fronts, the PFAS and the iridium. Next slide, please. And the European Clean Hydrogen Joint Undertaking itself has seen that these systems are markedly more cost effective. These are not the street prices of any of these technologies today, but AEM has the only ability to get below $100 per kilowatt, meet the 2050 targets. Next slide, please. And by energy arbitrage can really meet the hydrogen moonshot type targets. Next slide, please. And again, iridium has been identified as the most critical mineral when it comes to the energy transition that is not in abundance. We can replace this with something like nickel iron oxide, which is orders of magnitude more abundant and with exactly the same efficiency. Next slide, please. This is possible because running in electrolyte, you can activate 10 times or more of the catalyst that you can using a PEM system. So again, the superiority of AM electrolysis is actually in the design itself. Next slide, please. And we've demonstrated this for over a year with our 2nd generation. And next slide, please. And in our 3rd generation chemistry, we exceed the 2030 durability targets, which actually exceeds the durability of PEM and traditional alkaline today. We've tested these systems with NREL. Multiple OEMs are integrating these in whole systems. Next slide, please. And we're providing reference designs. So anybody who wants to work with us at all levels, including the test systems themselves, we can achieve rapid scaling. Next, please. And we are positioning to be a supplier to OEMs globally. We have production. We produce monomers at the half-ton scale today. We really are going for it in terms of scale up of this technology. Next slide, please. So thank you very much for your time and attention, and looking for your questions at the end.
Thank you very much, Ben. We will move on to the next presenter, which is Thomas Trevisan from Atmo. So I will give you the floor, Thomas.
Yes, thank you. Can you hear me? All good? Yeah. Thank you, Jonatan and ChemSec, obviously, for organizing this very interesting webinar. My name is Thomas Trevisan, and I'm Deputy Manager for Public Affairs, based in Brussels, and I work for Atmosphere. Next slide, please. Next one. What we are independent, we are global, and we work to accelerate cleanup, heating, and cooling with from a refrigerant perspective. Next slide, please. So what are refrigerants? Chemical substances, basically, that displace heat and provide cool, or vice versa. Your fridge, most likely, has a natural refrigerant in it if you're based in Europe, as a synthetic fluorinated refrigerant if you're based elsewhere. It might also have an ozone depleting substance if you're based in an Article 5 country according to the Montreal Protocol, which are developing countries. Next slide, please. So why are refrigerants important? Refrigerants have been labeled PFAS according to the new PFAS definition by the OECD. And they are important because they are, as we call them, the blood of every heating and cooling system where you mechanically control the temperatures. There you see the vapor compression cycle, and inside those coils, the refrigerant runs through and does the job of displacing heat and provide cool, or vice versa, if that is a heat pump. Next slide, please. As you might appreciate, refrigerants are basically everywhere. Anywhere you control mechanically temperatures and you make use of a refrigeration, air conditioning, or a heat pump, whether it's a stationary or a mobile system, you most likely will encounter refrigerants. And that's why refrigerants can be realistically basically anywhere. Next slide, please. Now, why are refrigerants a problem? In the previous section, the previous slides, you might have seen a closed loop system. Unfortunately, when that comes to reality, refrigerant leaks from operation, so from the vapor compression cycle. They can also leak from manufacturing facilities, and they also leak from landfills. That applies obviously for refrigerants that are PFAS and refrigerants that are not PFAS. But in this webinar, obviously, we're focusing on PFAS, and that's why refrigerants are important to address. Next slide, please. We've come a long way in terms of refrigerants. First, there were natural refrigerants, so basically natural working fluids such as carbon dioxide, hydrocarbons, ammonia, water, and air. But obviously there were some problems in terms of the system efficiencies back in the days. So then chemical industry came up with easier to use refrigerants such as CFCs, so chlorofluorocarbons, hydrochlorofluorocarbons, hydrofluorocarbons, and latest development are hydrofluoroolefins. Each of these chemicals, fluorinated chemicals, normally had shown problems related to the environment, whether it's the ozone hole, they created the ozone hole when leaking, global warming when it's related to hydrofluorocarbons or hydrochlorofluorocarbons. And now most of the new refrigerants with a low global warming potential are labeled as PFAS or degrade into PFAS. Obviously, as atmosphere, we believe this is a kind of a problematic chemical treadmill refrigerants, and we advocate for the safer uptake, for the safe uptake of natural heat carriers on the right side in green. Next slide, please, Jonathan. So in the big PFAS discussion, refrigerants to us are a very low-hanging fruit. Multiple companies are working with different natural refrigerants across a wide variety of application, regions, and temperatures. There you have kind of a schematic overview where you see CO2, ammonia, hydrocarbons, water, and air across different applications where you control mechanically the temperature, whether domestic, commercial, industrial, heat pumps, chillers, but also your cars. Beside natural refrigerants, there are also companies that are bringing to the market not in kind systems, so without relying on refrigerants. Next slide, please. The next 3 slides are a bit technical, so for the sake of time, I will just go through them quite quickly, but it's just to provide an overview of what are the synthetic fluorinated PFAS refrigerants that are used currently, and at the same time, what are the naturals that are used. Obviously, the PFAS are the problem, the natural refrigerants, if implemented safely, are the way ahead. So Jonathan, I think you can quickly skip this one. This one applies for heat pump and chillers. And next one as well. This is for cars. To be noted that HFO 1234YF decomposes 100% into TFA, another PFAS that is increasingly under scrutiny in Europe. Next slide, please. This is basically a message. we have alternatives. PFAS, HFOs, HFCs, CFCs are not critical, not essential to society. Natural alternatives can be implemented safely, so we should leapfrog in developing countries and completely get rid of PFAS and adopt other solutions such as naturals. Thank you very much.
Thank you very much, Thomas. Very interesting to hear about these alternatives as well. So we will move on to the next presenter, which is Christopher Christak from Transcene Company. So please, Christopher, if you can turn on your camera. There we go.
Thank you, Jonatan. Hello, everyone. Thank you for inviting me to the presentation today. We're going to discuss Transcene's journey away from PFAS chemicals that are used in electronic chemicals. Next slide, please. Briefly, I'd like to acknowledge our academic partners that participated in the research for this program. There's a group at UMass Lowell, sponsored and funded by the TURI Group, Toxic Use Reduction Institute. Next slide, please. Brief summary of Transcene. We've been in business since 1965, and we're primarily a manufacturer of electronic chemicals. We have some other product lines and diagnostic reagents and stains, analytical chemicals, but our focus is on electronic chemicals, specifically wet process chemicals. We have factories on both coasts in Massachusetts and also in California, and about 33 employees altogether. Next slide, please. So who are the electronics customers that we service? Everyone's familiar with large semiconductor fabs. There are well-known names, but there are also another tier of chip manufacturers, people who manufacture integrated circuits, MEMS, microelectromechanical systems, and really proliferating areas like photonics, optics, lasers, sensors. The whole Internet of Things relies increasingly on circuitry. Next slide, please. So this is the technical slide that I have for you. This talks about the role of surfactants in semiconductor processing, and the focus is on the photolithography process. And I'll run through this process for you quickly. In the graphic labeled 1, deposition, the customer will start with a substrate. It can be a silicon wafer or other materials like glass, silicon oxide, be silicon nitride, aluminum oxide, and they'll deposit one or a series of metals or other materials onto the surface in bulk. After that, a photoresist would be deposited, again in bulk across the whole surface. At that point, a mask would be placed on top of the photoresist or above the photoresist, and UV or sometimes EV radiation will be shined onto the mask. The exposed areas will polymerize. The mask is then removed, and a development step takes place, much like the film development process that we were all familiar with years ago. This will then leave a pattern of photoresist on the surface in step 4. This pattern of photoresist now serves as a new mask, and you can see the purple layer. There are exposed areas of metal now underneath the photoresist. Wet etchants are then applied to this construction, and they remove the metal selectively where it's exposed. And typically there's a final step where the photoresist is stripped away, leaving a patterned metal behind on the substrate. The PFAS materials are used primarily in the etching step, also in development and sometimes in the removal step as well. These solutions tend to be very specific to the type of material that's being removed. And I would say in perhaps 80 to 85% of the applications, no surfactants are required. But there are applications that do require them because they have difficult wettability properties, or there are complex geometries where it's difficult for the wet solutions to penetrate all the crevices or corners that are in the design. So the main function of these surfactants is to increase the wettability of the etching solutions so that they can provide a uniform etch result. The etch process also typically results in the formation of gas at the surface. So these gas bubbles will form at the surface of the metal and typically will be able to escape, to float to the surface on their own. In some solutions, the viscosity may be high, or there's just too much affinity at the surface, and these bubbles can stay behind. Where there's a bubble on the surface, the solution is not contacting the surface and the etching is not taking place. So the reduced surface tension allows these gases to escape. There are a lot of requirements for proper functioning of these surfactants. Primarily is there can't be any residue or contamination in the device. The semiconductor devices are very sensitive, and the customers are expecting a certain chemistry, and there can't be anything left behind after the etch or development process is complete. We need to have surfactants effective at a low concentration, typically around 0.1% by weight or less. And again, the reason for that is there are set parameters for etching. We expect a certain chemistry to etch at a certain rate and have a certain capacity. And if we have to load up on additives, it's going to create a different process. Foam is also an issue. We can't have too much foaming or bubbling. Naturally, surfactants tend to be foaming materials. So that's another area where we have to be careful. Next slide, please. Compatibility was a great challenge for us in developing alternatives. Our products tend to be strongly acidic solutions. Some of them are strongly oxidizing solutions with very challenging materials, whether it's nitric acid, hydrofluoric acid, silicon nitrate. These are all chemicals that are very difficult to achieve compatibility with. And so it's not so easy to find alternatives. We're looking for specific surface tension reduction. Most of the chemistries start out in the mid-70s, 75, 78 for surface tension. And we were looking to bring down the surface tension to high 20s, maybe low 30s millinewton meters, with, again, about a 0.1% surfactant concentration. In addition to the residue concern, we don't want anything left on the surface. Contaminants are also a concern. So sodium in particular is probably the #1 poison for semiconductor devices because it can migrate into the silicon and change the conductivity. And one of the challenges was that many of the surfactants that are commercially available are sodium salts of organic molecules. And so introducing sodium, even at a low level, would have been a very difficult sell for us with our customers. Compatibility is one side, but we also need stability. So it's one thing to get the surfactant to dissolve or be miscible with the solution, but it needs to be stable over an extended period of time, certainly greater than a year, hopefully more 2, 3, 4, 5 years, and stable under different conditions. We need to be able to ship during the hot summer months, during the cold winter months, and not have any impact on the shelf life of the material. I mentioned low foaming, and of course, cost is always a concern. Fortunately for us, the PFAS materials that had been used in surfactants, or we had been using, are quite expensive, on the order of perhaps $700 per liter. So we were optimistic entering this project that we would be able to achieve a lower cost. Next slide, please. How did we end up in this situation? I've been with Transene for about 20 years. And when I joined, PFAS, the octal version, was used across the board. Everyone used it, and it was very effective. It was a wonderful material because it accomplished everything. We could have one surfactant that was used in all the chemistries, very effective at low levels. But of course, that was the first PFAS type material that was targeted. Quite some time ago, it was clear it was being phased out, going to be banned by the industry. And so there was kind of a scramble to find alternatives. This was the classic example of regrettable substitutions, though, because the industry tended to gravitate toward PFAS materials. And another aspect of that was that these PFAS materials didn't have quite the same effectiveness as PFAS, and we ended up needing to tailor different surfactants to different applications, mainly to achieve compatibility and also end results. So we went from having one PFAS surfactant to perhaps 8 to 10 PFAS surfactants to accomplish the same result. Now PFAS, of course, has been identified as harmful, and it's time to eliminate that as well. So, the question was, what were we going to do next? Next slide, please. This was going to be a great challenge for us. Transene is a small company with some limited resources. We began by focusing on sources that we knew, surfactant manufacturers that we were familiar with or were commonly used in the industry. Fortunately, in Massachusetts, the state where we reside, there's a very strong governmental program to assist companies with identifying alternatives for environmentally hazardous chemicals. PFAS was very much on their list, so I reached out to them and was connected with a group at the University of Massachusetts Lowell, which is sponsored by the Toxic Use Reduction Institute of the state. And they generously funded a program where a research group at the university was able to work with us, put more resources to work, both in terms of just hands at the bench working on the project, but also with additional equipment to help us analyze the different candidates. So this group collaborative approach really accelerated the program for us. It allowed us to analyze a wider range of candidates and identify a wider range of candidates. Also importantly, the university had resources to help us vet the candidates that we were considering. Some might be able to be eliminated immediately because they weren't going to be favorable environmentally, but we could take a quick check at the outset to make sure something was worthwhile pursuing before we expended resources on it. Next slide, please. Well, all the work is wonderful, but if you can't gain customer acceptance, it's all in vain. So how did we go about the process of introducing and winning over customers for this? Customers use our products, particularly the etchants, in a variety of different ways. Some have immersion tanks with various degrees of circulation. Some will spray the product on, some will swab it on. So it needs to be useful in a variety of different methods. Transene has hundreds of customers in the electronics industry, and we considered how we could start introducing these. Some customers we hear from every month. They order monthly or quarterly or maybe a couple times per year. Other customers are ordering products really just for a single use. They might have a research project or they're trying to prove something out, and they haven't been purchasing it before, and they're probably not going to purchase it again. So these are the easiest targets because they don't have any expectations going in other than that we're going to provide them with a product that's going to etch effectively in their application. And in these cases, they knew they wanted something with a surfactant based on maybe literature results, something like that. So we began introducing the product to these customers. At the outset, we had a quick comment that the customer was experiencing some foaming issues, which is something that I alluded to earlier. So we dialed back the concentration a little bit. The foaming was reduced, but the effectiveness was still there. This phase went on for a number of months, and we often don't get an opportunity to engage with our customers to a great extent. If they're unhappy with something, they'll let us know about it. If all things are going well, we don't really hear from them. They just move on with their work. So there were no further complaints or comments, and we considered that phase complete. We moved on to another cohort of customers who I would say is more relaxed in terms of their approach. They're interested in knowing what's going on, but they don't have a rigid specification. They just want to know, okay, you've checked this, it works. This is an important change that needs to be made, and they're aware they can bring it in and start working with it. So we went through that phase with quite a number of customers, and again, no problems, no complaints. This has turned out to be a perfect drop-in. So we moved on to the final phase, and that's really the phase that we're in now. There are some very large customers who are much more rigid in their approach. They have extended qualification programs. So we've been ongoing for maybe 3 or 4 months at this point, and no problems yet, but still letting the process play out. In most cases, these customers need to use it in their process, create their devices, and then submit their devices to the next level customer to qualify and evaluate. So we're waiting on that, and I hope that by the end of the year, we'll have all of our customers converted. I did note that it hasn't been 100% success rate. We did have one customer that claimed it was leaving a residue on their parts, although I'm not sure about that, and they completely moved away from our product altogether. So not everything works, but it's been pretty close, and for most of our customers, we're approaching 100% success rate with that. I do want to mention, you might be asking, we're only adding 0.1%. This isn't a whole lot of material, but it really can proliferate. I don't know the details, but I know that a lot of our customers will treat the spent chemicals, and then they can flush them into public waterways. So even though we're using a relatively small amount here at our facility, it can really propagate rapidly by going to our customers and having them then disseminate it into the environment. Next slide, please. So in conclusion, we found that there was a great advantage to having an industry academic collaboration. It really accelerated the process, and I think introduced us to a greater range of materials than we otherwise would have looked at, and really helped us to find excellent candidates that were going to be successful in these different formulations. The takeaway lesson is that PFAS replacements are viable even in very challenging environments. There was an impact favorably on cost. I referenced the cost per liter of PFAS, around 700 euros per liter. Replacements are maybe 1/10 of that. So there has been a cost savings. Minimal sales impact, but we find a lot of customers are asking us more and more, are PFAS in the products you're selling to us? So it's a very big step in the right direction for us to be able to come out and say, no, our products don't contain PFAS anymore. Here in the US, there's, I think, increasing concern about liability as well, and eliminating the PFAS materials certainly reduces our liability and our customers' liability for the environment. All right, thank you very much for your attention. I'll look forward to questions at the end of the session.
Thank you very much, Chris. Really, really interesting. We will move on to the last presenter of the day, which is Nicole Hyun from Sympatex. So please, Nicole.
Yes, thanks, Jonatan. Hello, everyone. My name is Nicole Hyun. Thanks to ChemSec as well. I'm CSR manager at Sympatex. We are providing breathable, waterproof, windproof, functional fabrics for garments, footwear, and technical applications. And I'd like to present the performance and development of PFAS-free textile alternatives. Next slide. So to give you a short overview, I'd like to explain what are functional fabrics, talk about the performance of PFAS-free fabrics, and then how are we developing PFAS-free functional fabrics. Next slide. So here on the right-hand side, you can see a typical 3-layer compound, so-called laminate, which is made out of an outer lining on top. Then the orange one is the barrier layer, and then you have typically an inner lining. The outer lining is often treated with a durable water repellent treatment, a so-called DWR. This is what makes the fabric water repellent. It's a difference to the barrier layer, which makes the fabric waterproof. The waterproof barrier can be either a membrane or a coating, and both DWR and the barrier layer can be made by PFAS or fluorine-free. So both characteristics are, of course, important, and I'd like to show you how to test them. Next slide, please. So On the one hand, the water repellency is tested normally by the spray test, which is, say, has not many requirements. The Bundesmann test, the second one, is more demanding. This is what we are testing in general. And then you have the rain tower test. But this is not only about water repellency, but when when you have a garment, you can analyze whether the construction of the garment, the pockets or the zippers, etc., are waterproof as well. And what we found out is that by using today's fluorine-free DWRs, you can reach really good results, like for the fluorocarbon treatments. Only there might be slightly more frequent re-impregnation of fluorine-free DWR after washing necessary. When we have a look at the waterproofness, the test is called determination of resistance to water penetration. And there we can't see any difference in the different membrane or coating systems. The compact system is non-porous. For example, the Sympatex membranes, polyester membrane, but there are PU coatings or membranes as well, which are non-porous. The microporous systems have a bit lower performance regarding to the waterproofness because they are expanded. They have micropores. With that, they need a additionally PU layer on top in order to increase or improve the waterproofness. Next slide, please. So what I said is that we can reach a really, really good water repellency, but there are different parameters we have to keep in mind. So we have, in order to have an equal performance with the fluorocarbon DWRs. So with the correct adjustment of all parameters, you will achieve that. So you have to take into account the textile surface, the textile structure. Are we talking about a woven fabric, the yarn count, the yarn density, and so on? Secondly, the DWR recipe, then the finishing parameters in the production side, the machines, and then of course the intended use. So what is the application of the garment? When you take into account those parameters and have them properly balanced, you reach the same performance like for the fluorocarbon DWRs, even with the PFAS-free ones. Means we reach grade 5, 10 minutes Bundesmann test, even after 5 times 40 degrees washing, which is pretty good result. Next slide, please. And regarding the development of the PFAS-free alternatives, Sympatex started pretty early in 2008 already. We launched together with the Rudolph company the first fluorine-free DWR on the outdoor market. To be honest, no one was interested in, but this changed in 2012. There was an increased demand from customer side due to the Greenpeace detox campaign. So in 2013, we started to increase our R&D activities until today. We're regularly testing the available DWRs existing on the market. And we're doing this in 2 working groups. The one working group is testing the performance comparison of fluorine-free and fluorocarbon treatments, especially when we have a look at oil repellency and so on. And then the customer-orientated issues means, like said in the last in the previous presentation, the customer communication is really important. We're a B2B company, and we have to convince our brands as well. So this is what the working group is working on, and of course the benchmark. So we have a look at what are the competitors doing, and the different DWRs existing on the market. We're testing on Sympatex laminates. So I think that was it. Jonatan said I should make it easy and short. And I tried to do that.
Yeah, I did. You did that very good, I think. So thank you very much, Nicole, and all the other speakers. I will now stop sharing and showing your faces instead. So if the 4 speakers, please can just put on their cameras, and we'll take some questions. There are a bunch of questions, and we have some time to answer these questions. I will hand them out to you, and we'll see. And if there is, I will point them in one direction, but if you're anyone else, if you want to chime in, please don't hesitate to do that. So I will start with a question to Ben. It seems like you've obviously overcome a lot of different technological challenges that were at least said to be impossible. So what was your driver to continue in spite of these sort of so-called truths that it was not possible to replace PFAS?
In reality, both of these material sets were considered moonshots. They were enabled by a professorship that my professor received. And the driver was really a technological advance. The honest truth is, although I had been an intern of DuPont substantially previous, and I thought honestly that PFAS would be banned by 2015, that it was not actually to replace these at all. It was just to meet the long-standing targets of the US Department of Energy and NITO in Japan and the FCH-JU in Europe, and for high temperature systems, for more stable systems. And it was a pure technological driver.
Good, thank you very much. So we also have a question for Thomas regarding your presentation. So the question is, as the efficiency of the heat exchange process is important, can you please comment on the performance of the natural refrigerants compared to the synthetics?
Sure. I see a bunch of questions actually on F-gases, and I'm very happy to take them bilaterally, but maybe not monopolizing the discussion today. Regarding the question, we do not experience any lack. I assume this is in terms of energy performances, first off, and we do not have knowledge of lower energy performances when adopting natural refrigerant solution rather than synthetic ones. So if that is from an energy point of view and an energy consumption point of view, this is one of the myths that goes along in the industry at the moment, also for the revision of the UF gas regulation. But to our knowledge, there's no drop in efficiency, if that is what the question is about.
Yeah, I think that the question is about that. And I think that's something that's regularly talked about, that there is a drop in efficiency, but it's good to hear that you don't consider that the complete truth. And as Thomas said, there is a bunch of questions. We will try to answer some of them now. And I will send all the questions to the presenters afterwards, so they might have time to reply through mail instead. So we also have a question for Christopher. So was there a publication in which all of the vetted alternatives were evaluated? What didn't work is also important, as was finally chosen. I think you're muted now, Chris.
There is a publication that is going through the process. I don't believe it's been published yet in the Journal of Clean Technology that should be coming out. I don't know that it lists all the alternatives that weren't included, but again, there could be a variety of reasons. Some, a great number of them because of incompatibility or of sodium ion presence in there. But I'd be happy to share more information if somebody wanted to contact me directly as well. But I don't think there's a comprehensive list of the dozens and dozens that we tested that weren't suitable in these applications.
Yep. Good to hear, because I agree with that question. It's always good to know what has been tested, because as they said, it's almost equally important to know sort of what did not work. So we also have a question for Nicole. I'll just take it. How many washing cycles before the water repellency is reduced? Is there a difference to the PFAS versions towards synthetics?
That's a difficult question, I would say, because it depends on the fabric, of course, and I would have to talk to our R&D department. What's the current status of that? I know that in previous times it was lower, but for example, Hohenstein Institute sent us a mail or the answer that even for fluorocarbon DWRs, after 5 times you have to re-impregnate again. So this is something official, and that's something really interesting. I think that you have to keep in mind when you think about blaming fluorine-free DWRs. So, but I can ask the R&D department about the current numbers of washing cycles.
Yeah, I think it's always, I mean, that's when you have an alternative, will always be the scrutiny of the specific details of how it works for specific uses. But I think it's from the ChemSec point of view, I agree. I think that the important thing is that we can replace them, and of course we will not have the exact same product, but then that's more something we can communicate around what the differences are.
The fit for purpose approach, let's say.
Yeah, exactly. So I see we have some time left, so there are a bunch of other questions. So I have one more for Ben. So a large amount of PFAS-based ionomers are used in chemical electrolysis, such as chlorine alkali. Do you have solutions for these applications as well?
For essentially every application that uses naphthalene or other perfluorosulfonic acids, we have alternatives, or in specifically chlor-alkali, which I would consider the most difficult case because of the direct production of chlorine, which will chlorinate your hydrocarbons. There's something called the E-shuttle process, developed by a company in California that was invested in by Khosla Ventures, that can get around the use case of existing chlor-alkali. There are alternative, slightly less beneficial chlor-alkali technologies as well that do not require these materials. Other major use cases like flow batteries, absolutely.
Thank you. So I'll just see. I can take another question for Thomas. Regarding PFAS as refrigerants. Do you think it would be possible to make another amendment to the Montreal Protocol, or is it more effective to regulate these PFAS compounds in a PFAS restriction? Which way do you think is the best way to go forward?
Well, this is a very good question. So just for a matter of fact, we will organize an event in Bangkok later, early July, under the Montreal Protocol, talking about PFAS and refrigerants. But we have to say that from our perspective, it's much easier to start from Europe and through REACH rather than amend the Montreal Protocol. We believe it's a faster way because the Montreal Protocol takes a long time before reaching every amendment, as it was for the Kigali Amendment. So yeah, this would be my take on this.
Thank you very much. I'll have time for one more for Christopher. So when using PFAS surfactants for development, etching or photoresist removal, are there any PFAS residues, especially above the planned limits in REACH restriction proposal? So do you know about that?
Yes, I'm aware of it. These are completely miscible, and they're removed during the rinse process. So after etching or development takes place, there's a rinse step, which is designed to remove anything that's left behind. So they stay with the original solution and they're also miscible with the rinse water. There's no evidence of any being left behind. And
is this rinse water then reused, or what is the process?
Well, that's up to the customer again. I think that many of them would combine it with their spent etchant solution. Maybe they reuse it once or twice, but they would, because it will begin building up residue from what it's rinsing off. So at some point it's not clean water that they're rinsing it with. So I believe it's usually combined with their spent solution. And then depending on whatever their process is, they're either disposing or they are neutralizing and flushing into the municipal water.
Thank you. I will take one last for Nicole, and then we'll see if we have maybe time for one final question. So, Nicole, what about oil repellency? I think this is a classical question. So what about oil repellency? Have you developed oil repellent treatments that can perform as well as the PFAS ones?
Yes, unfortunately not. But again, we need to have a look at the fit for purpose approach. And I think that for many applications, oil repellency is not necessary. And for the ones that where we need oil repellency, we have to take fluorocarbon or the normal current use DWRs. But there's a lot of R&D happening at the moment and since the last years, and I think it's just a question of time, and we have an alternative. So this is something we're working on, but let's say the excuse that we need oil repellency in order to use sun cream and stuff like this is, not justified. So.
Yeah, I assume that you've had that question before, and again, I agree. I think we have to look at the function and what we need for the different garments and other we use. I would like to end with, if it's possible for you to just very briefly, not everyone has to answer on the presentators, but if you want to. So we always get this question regarding alternatives. Are they really safer? So it would be interesting to just post that question to all of you. So how do you make sure that the alternatives you're using are safer, so we don't end up in regrettable substitution, for example? So please, if anyone wants to start with a brief answer to that one.
I'd be happy to make a comment on it. That was one of the great advantages of our collaboration with the university, in that they have tools for just such a question, and that was part of our initial evaluation of candidates. As we would come up with ideas that we wanted to test, they were quickly run through the tools that the university had, and we were able to confirm at the outset whether that was something we wanted to pursue or not. So we did confirm that these are all more environmentally friendly and safer materials.
I had linked 2 papers in one of the Q&A, but it seems to have disappeared. But we conducted detailed degradation studies and sequences, and also have had partners do the same thing. And so we guaranteed that all of the breakdown products are actually pretty non-toxic.
Thank you. So anyone, Thomas or Nicole, want to say something? Otherwise, I think I will wrap up.
Very quickly, Jonathan. I mean, the chemicals that are used as natural refrigerant are not persistent, and the drawbacks are very well known by the industry, and they are managed. And there are no big surprises if you use CO2, ammonia, hydrocarbons. You know, the one is toxic, the other is high pressure, and the other can be flammable. So industry knows that. There are no degradation products that may end up being problematic. So that as easy as that.
And for technical textiles, I think for DWR, we still have to determine this, but for the membranes, we all know that what PDFE causes during production and for recycling, and I think that polyurethane and polyester are, on the one hand, more environmental friendly materials during production, and furthermore, like polyester can be recycled, so we have closed cycle system, which is always better.
Exactly. So we're running out of time. I would like to just one comment before we wrap up, that the slides and a recording of this webinar will be made available on our webpage and also sent to everyone who's registered for the webinar. I would like to thank all of the presenters for a very, very interesting presentation, and thank you for answering all these questions. And I thank all of the attendees for listening in, and I wish you a great day, and see you on the next ChemSec webinar. Thank you very much.
Thanks.
Thank you, everyone.
Thank you.